Yes, today we're looking at more exponential growth and decay. It's very similar to what we talked about with the compound interest yesterday. Actually, it's about the same formula for continuous growth. Yesterday it was A equals PE to the RT. Today it's N equals N naught E to the KT, or N sub 0 E to the KT. So if you notice, it's just N and N naught instead of A and P, and then K instead of R, but it is the same formula. K is called the growth constant, and that's growth when it's positive. It's decay if it's negative. N is the final amount, just like it was with money, and N naught, just like principal, that is the starting amount. So we're going to look at exponential growth. Here we are, year 2001, and we're given the formula. So, what did your company pay for the property? So that was, if you bought it T years after 2001, you bought it in 2001, so that means T equals 0. So when we plug in 0, there's actually an easier way than just plugging in 0, because plugging in 0 makes e to the 0. Anything to the 0 is 1, so we are left with just 500. But also we know that because that number right there is always the starting amount, and that in this case would have been what you paid for it. So the value of the property is in thousands of dollars, so it's $500,000. By what percentage is the price of the property increasing per year? Also, just like we talked about yesterday, this number, the R, was the rate at which it was increasing. K does the exact same thing. So that 0.055 is the percent that it's increasing by. So that is 5.5%. And what will the property be worth in the year 2010? So if it's T years after 2001, 2010 is how many years after 2001? That'd be 9 years later. So we're plugging in 9 now. So we'll get out our calculator, plug in 9. So we're plugging in 9 for the year into our formula right there. So that's starting with e to the 0.055 times 9 times 500. We get 820, 249. Remember, this was thousands of dollars, so we can keep 2 more numbers there for the pennies, I guess. So that'd be 0.12. There you go. When will it be worth $750,000? Well, it's obviously going to be before 2010, because we're already at 820 in 2010. So we set the 750 there into our formula. And we're going to solve for t. So first thing, divide by 500. That is 1.5. And then to solve this, since we have the variable in the exponent, we're going to natural log exponents to the front. That'll be natural log e. And you should remember that natural log e cancels out. That's just 1. So divide by 0.055. So natural log 1.5 divided by 0.055. So this is giving our answer in scientific notation. That's the e negative 3. That doesn't seem right. Nope, because I didn't get the decimal in there. .055. Yep, so should be 7.372. So that would be years. Those were years after 2001. So add 7.3 years onto there. That would be sometime in 2008. Half-life is the amount of time that it takes for half of the sample to disintegrate. Very similar to what we talked about with doubling time with the money in our last lesson. So if we start with 10, then after the half-life has completed, we'd be left with half of that. We'd be left with 5 grams if we started with 10. So this doesn't tell us, it just gives us the equation here. So that's what we really need, though, because this is how many grams will be present after 25,000 years. So that just means we're plugging in 25,000 for t. And obviously this is decaying because it's a negative. And again, plugging in 25,000 for t. And then times the 10 that was in front. So we get 0.486. So we started with 10 grams. After 25,000 years, we have a little bit less than half a gram. What's the half-life? So to find the half-life, that means how long would it take for half of it to be left. So we start with 10, we end with 5. And we are solving for t. So since our variable's in the exponent, we want to first get that by itself. So 5 divided by 10 is 1/2, which is going to be very common in half-life. That's the way it's going to work out, because it's half-life. And then we would natural log both sides, exponents to the front. And again, natural log e is always going to cancel out. So we divide So it's natural log of 1/2, or 0.5, divided by negative 0.000121. 5,728. It was about 0.5 years. You could have said 0.489 years if you wanted to be a little bit more precise. So it takes about 5,728.5 years for half of it. That's the half-life. All right. This one says we start in biology experiment. Starting with 1,200 bacteria, 4 hours later there's 2,200. Is it a growth or decay? Well, it went up, so it is growing. Determine the growth constant K. Whenever it says growth constant or decay constant, that means you're just finding K. So we know that we ended with 2,200. We started with 1,200, and it's e to the kt. And we are told t is 4 hours, so we can plug in a 4 right there. So we're going to solve this out, divide it. You get 1.8, or you could leave it as a fraction, 11 over 6. And then again, the variable's in the exponent, so we natural log both sides. Move the exponent to the front. Natural log of e cancels out like always. It's 1. So then we'll divide by 4. Natural log 11 over 6. Divided by 4. So 0.1515 is our K, our constant. Now what I like to do is store that as the letter K, just to keep this as precise as possible. I don't want to have to keep retyping that, and I don't want to lose all these extra digits that we had there. So our formula to tell us how much will be left after 3 hours, or how much bacteria there would be after 3 hours, we know 4 hours it was 2,200, so it's going to be somewhere a little bit less than 2,200. So we want to know how much there will be starting with 1,200, e to the k, which is this number we just found. And we're plugging in 3 hours. Now remember, we saved that 1515 as k, so we can type that in just like that with the letter k. So it's 1200 e to the k, because that's what we saved it as, times 3. And that makes sense. We said it would be probably a little bit less than 2,000, because it definitely had to be less than 2,200. That number is 1890. You could round that up, if you, or you can even just keep the decimal. It doesn't really matter. Won't be too picky about that. When will the population reach 3,000? Well, we know it's going to be more than 4 hours. Probably 5 or 6 hours would be my guess. But we will solve it out. Plug in 3,000. And we are solving for t again. So since that's in the variable, we're going to get everything by itself and natural log both sides. So those zeros cancel out. 30 divided by 12, less buttons to type in. It's 2.5. Natural log both sides to get the exponent down. Move the exponent to the front. Natural log e always cancels out. It's 1. So then we divide. So we get t equals natural log 2.5 divided by, and remember that number is k, so I'm just going to do alpha k rather than typing that. So that's 6. I think that was what I said a good estimate would be. I said it would definitely be more than 5, more than 4, probably closer to 6. And that's almost exactly what it was, 6.047. Alright, so this time we need to come up with the formula entirely. It just gives us the information. We know that in 1988 it started at 350, increased by 0.4% per year. So it started at 350, increased at 0.4%, which would be 0.004 as a decimal. And then, assuming that rate continues, when will it reach 600? We're solving for t to answer when. So we'll divide first. 600 divided by 350. (12/7). And then again, trying to get rid of the exponent, so natural log both sides to bring it down. Exponents to the front. Times natural log e, which every time natural log of e is 1, it cancels out, doesn't matter, get rid of it. So natural log of 12/7 divided by 0.004. $134.749. So that was per year, so this is how many years? 134, almost 135 years. And that will be just starting after 1988. Because 1988 was our starting amount there. So all we need to do is just add 1988 onto that. Oops, too many times. So the year 2122. That would be the year, according to this, that it would reach 600 parts per million. How long will it take to double? So if we started at 350, that means double would be 700. So we divide. Obviously, when we divide this, we're going to get 2 because we're doubling. Then we will natural log to solve for the exponent, and then exponents move to the front, and natural log of e will cancel out. So natural log 2 equals 0.004t natural log e. Again, natural log of e is always 1. It cancels out. And then we'll divide by 0.004. $173. So 173 years. How long will it take? That's how long it will take, 173 years. We don't need to put it as to what year it will be, just that it will take 173. All right, last example, and then we'll just wrap a couple things up. So the half-life of iodine is 8 days, so determine the K constant. So let's actually go ahead and jump to our last part right here. Half-life formula and double time formula. You can summarize these two things. We did these both. Whoops. A little bit today, a little bit yesterday. Half-life formula equals, I always just go to this part, and you can do KT or RT, it doesn't really matter. Double will be natural log 2, half-life will be natural log 1/2. Both times it just equals KT. You can go one step further and say over K on both these, and that equals T. I think it's easiest just to leave them right here. It's easiest for me to remember, at least, that they're both KT, and then it's just half for half-life and 2 for double. That's it. So determine the K constant, K, for iodine. So we're told that the half-life, so natural log 1/2, equals KT. We're trying to find K. We're told T is 8 days. So T is 8. Then we just solve that out. Super easy. Using that half-life formula. Natural log of 1/2, or 0.5, divided by 8. So K, for the decay constant, is negative 0.866. How much of a 2-gram sample will be left after 20 days? Now, when you think about that, that's like 2.5 half-lives. 8 days, it goes into that like 2.5 times. So it's going to get cut in half, and then cut in half again, and then not quite half, but it'll be cut a little bit more. So if you cut that in half, you go to 1, cut it in half again, you go to a half, and then a little bit more. So our answer will be less than half a gram. But we'll actually work it out with the calculator, not a big deal here. We now know K. If we start with 2 grams, we know K is negative 0.0866. We're plugging in 20 days. We're just working out that equation. So since we have our decay constant right there, I didn't save it as K, but we could do, since we only need to use it once, that's okay. We can just do shift answer times 20. So that takes care of our E part. Then we have the times 2. That's the only part left in our formula. And let's see, what did we say? 3536. Which fits with what I said. I said it would be less than half of a gram because it gets cut in half, and then a little bit more. Last thing, I started actually showing it at one point. Let's just say this divided by, this should work out. I just want to point out this notation just to review for you. Scientific notation on your calculator does that little E -4, which means the same thing as times 10 to the -4, which would mean just move your decimal 4 spots to the left. If that was a positive, you would just move it 4 spots to the right. That's just scientific notation. Quick 30-second review of that for you. All right, that's it. Post your comments, like this video, all that good stuff. Most importantly, get your assignment done that goes with this and submit it to me. See you next time.